Welcome to our second lecture on the course Solar Electric Energy Systems. We talked about potential irradiance and shadowing and so on in the last lecture. Today we'll talk about solar concentration and solar thermal systems. So solar thermal systems are known for a quite long time. Here even a quite advanced solar thermal system at the World Exhibition in Paris in 1889 with a parabolic concentrator, steam generator, and on the left you see a steam engine which is driving a printing press. Got lots of success during the time. Also smaller systems, first as flat plate collector was patented in 1910, so it's a quite established technology. Today we talk about concentration. So we have here as an example the parabolic concentrator. So you have the effective area from the sun coming in. In general, a parabolic concentrator can only concentrate direct solar irradiance, cannot make use of diffuse irradiance. So we have the effective area. The irradiance is then reflected on the focus area here. Here the absorber area could be a point or could be an area. According to that, here you see we have the concentration ratio, which is the absorber area divided by the aperture area. You don't have to make a single mirror like you see here on the bottom. You can also make a parabolic truck. So you don't have a focus point, you have a focus line here. Also, you can split up the parabolic form in different reflectors or make even several small reflectors. The only thing is that they have to be attached in a tangential form around the parabolic form. And then they must be positioned in that way that all incoming light is reflected towards the focus point or the absorber. Here you see the different concentration ratios, starting with 1, that means no concentration. That's a conventional flat plate absorber. It is able to achieve a temperature in the vicinity of 160, 180 degrees. Sure, at this efficiency, if you have a collector and you want to achieve the maximum temperature, you shouldn't push any water through it, and therefore the collector efficiency is 0. If you let flow a lot of water through it, then efficiency goes up, but then the achievable temperature is much lower. So if you follow this line going up, achievable temperature is very low. If you go to higher concentration ratio, for example 10 here, temperature is much higher, so it can be above 500 degrees. If you have an acceptable efficiency, you should count on 300 degrees or so, and so on. So you concentrate more and more, and you can have really high temperatures. The theoretical maximum is the temperature of the surface of the sun. So it's not possible thermodynamically to achieve higher temperature than your source, which is the sun, and this is 5,770 Kelvin. And there you have a concentration rate of about 30,000. Here you see an example, interestingly from the 50s and 60s in southern France. Before France started to invest a lot of nuclear energy, they were very well advanced in solar energy. The opportunity to go there, it's on the border to Spain and the Pyrenees. It's called Four Solaire in Odeo. And this is a quite high building, about 40 meters. In front of that building, there are 63 plane mirrors, which direct the changing sunlight. They are always tracked to the sunlight, and they direct it in such a way that the sun rays go in parallel to this big parabolic mirror. And then you have a concentration here, the end of a factor of 16,000 concentration ratio. That means you have a power density of 1.6 kilowatt per square centimeters, not per square meter, per square centimeters. That's really a lot. The maximum achieved temperature there was 3,000 degrees Celsius. The efficiency was about 60%. It has been used in the beginning for producing steam, powering a steam generator. Nowadays it's used for metallurgy because you can switch quickly off and on the power source, the mirrors, and then you can have different mixtures of metals and so on, treat them with different temperature, and therefore it's still under operation. It's a bit newer example from 1985 in the Mojave Desert in Arizona in the United States. It's been built during the government of Jimmy Carter there. It was for a very long time the largest solar energy plant in the world. In the end stage, it had about 354 megawatts electric with a mirror area of 2.6 square kilometers. Interestingly, the mirrors have not been made in the United States. They came from Germany, from the company Schott. They require a lot of cleaning because there's sand and so on, so the operations costs are relatively high. At the end, the total electricity costs have been around 10 cents per kilowatt hour. And in comparison to photovoltaics nowadays, that is quite a lot. So the last quotes for, I think it was a big Qatar power plant, the last offers there have been in the vicinity of 1.4 cent per kilowatt hour for photovoltaic power plants. So let's go into the power flow. So the first part you know very well, incoming irradiance. We are discussing this a lot in the last lectures. Then you have the reflector, something lost because it's not perfect reflection. Here this is the index rho. And then it hits the absorber. There's also some losses there. Usually the reflector is quite close to the absorber. But for example, if you have a tower power plant, then this could be in some distance here. So we saw here before. So this could be some 100 meters, and therefore could be even some losses here. And as is mentioned here. And then you have the absorber, which is protected via, for example, here a glass tube here. When the absorption is not perfect, you try to make this alpha as high as possible to achieve the maximum absorption. And here it's converted the incoming irradiance into heat. You try to profit a lot from this generated heat, but you have some losses. For example, thermal radiation or convective heat transfer. Depends. Sometimes you have this glass tube evacuated, so you have a vacuum inside. So inside there is no convective heat transfer, but outside there's a convective heat transfer. So cold air comes here, it gets heated up, density gets lighter, so it flows up. Therefore, you have quite a high share of convective heat transfer. You don't have to concentrate via parabolic mirrors. You can also use lenses, or kind of flat lenses called Fresnel lenses. In general, if you take a look at the scheme of energy flow, so we have here talked a lot about the incoming irradiance and some part is reflected. Then we have the solar energy converter here, which also requires some energy to be produced, the so-called gray energy. In photovoltaics, what we discussed next lecture, this is the green energy flow, this is the electric output. In general, what we discussed today is the thermal flow, so small q we use for that. So we can either store that energy or we can take away, we have water flow, or in general, the lower ones are losses, conduction due to the imperfect damping. You have radiation, that is thermal radiation with the surface temperature of the collector, or convection, as I just mentioned. Here you see typical loss mechanisms in a solar thermal flat plate collector, so without concentration. So we see here we have a reflection, that's a cover. If you come from air to glass, you have a reflection here at the first interface about 4%. Depending on the thickness and the quality of the glass and the incidence angle, you have some absorption in the glass, typically 2%. And then at the next interface, from glass back to air, you have typically another 4% of losses. So in totally, it's about 8% of losses at the first cover sheet. If you have two cover sheets, it's a double. And usually nowadays we have only one cover sheet. And then it hits the absorber. As I told, the absorption is not perfect, so we have some losses there. Here about 8%. And then also we have some, first then it gets transformed into a thermal heat flow. So we profit 60% of that. So this is our efficiency here. But we have also losses, thermal losses here. This is a thermal conduction, but also thermal radiation from the absorber plate. This can be reduced by the cover glass. So usually glass is transparent for the visible part or for sunlight, but not transparent for the infrared part being emitted from the absorber, the typical greenhouse effect what you see here. Plus we have the natural convection losses. As I mentioned, cold air is heating up, it's lifted, some buoyancy occurs, and new cold air comes, and we have this natural convection flow here. You can eliminate that by taking away the air here. So if there's no air, there's no natural convection. This is called vacuum collector. But on the other hand, you need a much thicker glass, a cover glass, or even a tube in order to withstand the pressure. So this is the upper one. This is a reflection at the absorber and absorption in the cover glass we call optical losses. The lower ones here, conduction and natural convection and the thermal radiation, these are called thermal losses at the collector. So you see here an overview. So we have here on the x-axis the temperature difference between a collector and ambient. On the y-axis we have the relative conversion efficiency. The blue part here are the optical losses. They are independent from the temperature difference. So you see here it's in the vicinity of 84% or 83%. It's a remaining relative conversion efficiency, so we lose about 16% due to the optical losses. Then, depending on the temperature, so sure, if you have no temperature difference here, there are no thermal losses, so you just have the optical losses. But as you increase the temperature, depending on the construction, we come to this later, it's a bit non-linear, because if you have high temperature difference, the thermal conduction is linear, but for the thermal radiation, it goes up with a power of 4. And so therefore this is a bit curved and not straight here. Here you see for an irradiance value of 1000 watt per square meter, you see this curve to achieve temperature difference about 100 degree Kelvin and still have an acceptable conversion efficiency. If the irradiance goes down, for example, winter, you hardly, even if with very low conversion efficiency, you hardly arrive at 40 degrees of temperature differences. Here we see the different types of solar thermal collectors. The red line, as I mentioned already, this is a vacuum tube collector. So we have very limited, or we have no convection here, and therefore the thermal losses are pretty much reduced. We principally have only conduction losses and thermal radiation losses. So you can achieve very high temperatures, well above 200 degrees. And the opposite, we have an uncovered absorber. So it's just a black tube here without any glass, and so this has this curve. Interestingly, you see here the optical losses are quite low. That's because you don't have any glass sheet, so there's no losses, no optical losses at the glass sheet. You just have the 9% absorption losses here at the surface of your absorber. But then the thermal losses are really, really high, and then temperature is sinking pretty quickly. You still can make use of this collector. For example, it's very often used at public swimming pools, where you just have to increase temperature maybe by 5 degrees. It's cheap, and in these operation range, it's even better than the more efficient flat plate collectors. Let's take a look at the flat plate collectors. So if you want to have a good efficiency, you take a 2-glass collector, so you limit the thermal losses there. But on the other hand, as you see here, you have a very high quantity of optical losses here, because due to the reflection on the interfaces between the different glass sheets and air. So it just makes sense if you have quite high temperature differences. Then we have two kinds of flat plate collectors, both with one glass, but one is called selective and the other called non-selective. Here the dark blue here, that is that one, and the selective apparently is much better, and I'll explain you now how this works. So here we have a logarithmic representation of the wavelength. The maximum of this is the solar radiation here. This is the sun considered as a black body, and the maximum of emission is in the vicinity of 500 nanometers or 0.5 micrometers. It seems to be symmetrical. As you saw with a linear scale, it looks much different. Then you have this black line is a non-selective absorber, so it absorbs all pretty much close to 1. So it absorbs in the visible range, but also here, as you see here, 10 micrometers, that's the infrared range. So it absorbs all the same. And there is a law that says that the absorption is equal to the emission index. So this alpha is equal to epsilon. So that means he has a good absorption, but in the infrared range has good absorption. That means, but also has a high emission. So that means the infrared radiation is emitted very well. So we have a very high quantity of losses here in the 10 micrometer range. This is a black body radiation at 350 Kelvin, which is a typical surface temperature of an absorber, a non-concentrating flat plate collector absorber. So what can we do? We make a so-called selective absorber. That means it's pretty much the same properties in the visible range, where we can absorb all the sun radiance, which goes up to 2 micrometers maybe. And then this changes its properties. The absorption goes down. That means also that the emission is going down also. So we have here quite a low emission and low absorption. And that means we avoid thermal losses. Sure, we cannot absorb anymore, but there's no solar irradiance anyway there. So in general, we have a big increase in efficiency here. As you see here, this middle blue line is well above the dark blue line here. So we can achieve much higher temperatures. At the highest temperature, you have the lowest efficiency. This is controlled by the flux of water. So if you have the so-called still stamped temperature, so you block the flux of water, then you achieve the highest temperature. But if you don't take away some of the hot water, then efficiency is sure it's close to zero. While you have the highest efficiency at the lowest temperature, you push a lot of water through the pipes, and there's not really a lot of time to heat up, but the thermal losses are low, and therefore you have a high conversion efficiency. That explains the behavior at the relative conversion efficiencies. So this is a very typical thermosiphon system. So you have the collector, and then you don't have a pump or something like this, just due to the fact that the heated water is lighter than the cold water. It automatically flows up. It's called buoyancy, and then we have here the hot water, which flows inside the storage tank here. The power of this flow is very low, so the height is very limited, so about 50 centimeters. And also you cannot make a lot of curve with this pipe, so the pipe has to be pretty straight, otherwise it won't work. So the auto circulation won't work. You see a lot of projects like this because people don't care about this, and they installed a thermal collector, but they didn't consider the limited height and the necessity to install a straight pipe here, and then it won't work. And the end you have both hot and cold water tank actually, but while the flow is very slow, you can have a very good stratification here. So the upper part is filled up with hot water, and the lower part is filled up with cold water. And astonishingly, the water doesn't mix a lot. If you don't have quick movements with the water, it stays like this, and you can take away the heated water and fill up the cold water on the lower part. Some examples here. Here you see the attached storage. Typical collector size for families between 2 and 2.5 square meters. I think this is a Turkish brand. It's also exported to Brazil. It's about 800 euros. Complete system. Weighs 42 kilograms, and you have the still temperature of 200 degrees Celsius. So another example is seen in Portugal. On the right side is a local produced system. On the left side is astonishingly imported from Australia, solar hard system. This is seen in Brazil. Also, this is integrated, so the storage system is directly attached to the collector. In Germany, the thermosiphons principles are not possible because in winter we have very cold outdoor temperatures, and the water inside the collector would freeze and would destroy the collector. So equivalent to a car cooling system, we have to have a medium with a mixture of glycol to withstand the cold temperature. Usually it's designed to go down to minus 25 degrees and so on. It works, but you cannot use glycol for taking a shower. So you have to do a heat exchange of the heated glycol with the conventional water here. And while the heat exchanger requires some pressure, it's not possible anymore with the thermosiphon principle. So you have to have an extra pump there and an extra control, because you cannot let run the pump for 24 hours, because in nighttime you would have the opposite effect. Outdoor could be very cold and you would cool down your storage tank. So you should switch off your collector, and what you do, you take the temperature difference between the hot part of the collector and see whether it's still higher than the water in the water tank. If it's higher, you switch on the pump. If it's colder, you keep it shut, the switch here, and then there's no pumping. You wait until the temperature is increasing. So you have also the hot water storage as a stratification tank. You take off the hot water. Plus, if you have really cold days and little irradiance, you have an additional heater there.